I'm still waiting for a cue from AV, but I guess I can start with our morning announcements first. First off, one of our sponsors this year is Zeta Labs, and they are hiring interns and full-time staff, so if you're interested, you should keep an eye open for them. Also, today at lunch in the BOF room, or Bird's Feather on the third floor, we're going to be having an info session about JuliaCon organizing for 2020, so if you're interested, you should come out for that. Also, we've switched the talk order for our first and second talks, so this morning we're going to be having Jeff open for our keynote. And other than that, okay, we're going to wait a second before we can get our live stream up and going. Yeah, we're ready? Okay, great. And so with that, we're starting today with Jeff telling us what's bad about Julia.
All right, thank you, Jane, and thank you, everybody. Thank you all for being here. It's great to see everyone. So I've loved seeing all the enthusiasm and great stuff about Julia, so I think it's time to turn it around a little bit. Let's balance that out. I personally love negativity and criticism. To me, that's the essence of progress. And I'm also not much of a morning person, so the negativity is going to come quite naturally. So this is, Gripes is my favorite Slack channel. I love it. So, and this is kind of this talk is sort of my extended griping session. And this is my favorite issue label. Keno filed an issue one day that inspired us to create this label. So a couple disclaimers when talking about things that are bad about Julia. So I don't know everything that is bad about Julia. In particular, I probably don't know why it's bad for you or why you have trouble with it or can't yet use it for something you want to use it for. I probably don't know that, but I would like to know. So so tell me. I can only tell you sort of from my perspective, things that I know about. So I don't know everything. So there are a lot of kind of well-known items that are sort of perennial annoyances, I think, for people in the Julia world. And just so you know that I am aware of them, I've just, I wanted to kind of go through all of them just so you know I know. So of course there's the time to first plot thing. We want better ways to build static binaries in libraries, better support for immutable arrays. People have made immutable array packages, but a lot of things in base kind of assume mutability, and it can be annoying. Generally, issues with mutation, how do I know what's safe to mutate, is a common stumbling block people run into. And we need better array optimizations. Far too often, to get good performance, you need to manually use in-place operations to get really high-performance array code. So we should improve that. And also people, I find, always want some sort of a protocol system. So, if I want to implement something that acts like an array or a string or what have you, what do I need to implement? We don't have a formal way of writing that out that really clarifies it. Harrison Groden is really thinking about this. I had a really good chat with him the other day. He has a lot of ideas. Hopefully something will happen there. And similarly, might be the same system or a different system, but some sort of traits so we don't have to have these big unions of listing out all the examples of a type. We can just add a declaration after. It's a big issue in the array code, linear algebra, and many other places. Also, the parser error messages need to be a lot better. Very common complaint. Other error messages in general could be a lot friendlier. Macro hygiene has a lot of really annoying corner cases. People run into weird problems with it a lot. There's a macro issue filed probably once a week or something, maybe more. And I think we're missing some notation. So like for instance, you can write out a vector perfectly fine, and you can write a matrix perfectly fine, but we don't have really a nice notation for ND arrays. And some things don't have nice printing. And also in the system, it's kind of unsatisfying. We have a couple types that are sort of special. So for instance, the sort of built-in array and string types, they work well, but you can't actually make a user-defined type that uses the same kind of memory layout tricks that they do. which I really don't like. Anything that's in the language, you should be able to make your own version of as well. That's sort of a philosophical point of ours. So I think we will fix that. Probably some sort of way to do objects that are variable size and have a variable number of fields is probably what we'll do at some point, I hope. And then, of course, there's the famous problem of something like map over an empty collection, where, I don't know what the big deal is, just return any or something. But, people want to get a certain element type, but there are no elements to compute on. So given the dynamic typing, you don't know how to come up with the type. So that can be kind of annoying. And then, of course, the whole missing data thing. We try to use missing, but there are cases where data value works better. And this is annoying to have the two kinds of missingness. And then there's also nothing. And and then there's more stuff. There's stuff about variable scope and, printing types as too verbose, and you get this unreachable reached message and it crashes, and packages need better conditional dependencies, and there's both the import and the using keyword, which is annoying and confusing, and there's things with trying to use packages and along with distributed computing on a cluster and what gets loaded where, and it's very annoying and it doesn't really work right. And when you compile code, it comes out too big, and memory isn't zeroed when it's initialized, and we don't garbage collect code. So if you're doing code generation, you can actually start filling up memory, and we need mutually recursive type declarations. That doesn't work. Keno is working on it, fortunately. And we need better tutorials and documentation from various different perspectives. Maybe we need some kind of static typing. Can we have that? And always more performance. Always more performance. It's never fast enough, is it? But So actually, I'd like to know by show of hands how many people feel bothered by one or more of these things. Okay, that's pretty good coverage, and better, more useful for me maybe is how many people feel that this is exhaustive. This covers basically everything that they have a problem with. Ooh, oh dear. Okay, I see, as I said, I'm going to clearly have to collect a lot of additional feedback. Well, yeah, come find me and gripe. But actually, I'm not going to really talk about any of that, because that stuff, that's sort of the known stuff. I want to talk about some things that are weird, that people don't talk about so much, but that I think are kind of bad and bother me, and maybe they don't matter as much. But I think they're kind of weird and interesting corner cases, which is what I kind of really want to talk about. So some stuff about modularity. So a typical Julia module extends functions in another module, like adding a method to base plus. And that lets us compose things and get lots of new functionality for free, which is great. That's basically always what we want. So that's totally fine as a default. But what if you didn't want that? What if you wanted to have sort of separately compiled modules, if you will, that were kind of totally sealed and fully baked, and you could understand everything that was going to happen in them. Nothing was going to interfere with them or extend them or anything, for a variety of reasons, either for predictability or just to reduce compile time or something like that. What if you wanted to sort of seal things off and have really isolated modules? Can you do that in Julia? So just to illustrate, this is the normal case where you can have two packages on top there, like intervals and diffyq, that don't know anything about each other. They don't use each other or reference each other in any way, but one can extend a method in base, and the other uses that function, so they can kind of communicate by extending common things. And so the key thing is that there is a line here that crosses from one module to another, right? But could we have these be totally isolated? Could we use a version of Julia where there weren't any of these edges crossing between modules extending each other? So there is kind of a case of this. This is not something people do that much, because of course they want their plus definition to be usable by other code. That's the whole point. But there is one case where we kind of do this, which is in the core system. So we have this module called core, which defines just the very few primitives you need to do anything, like the any type and the int type, and your basic functions like type of and isa and all of those things. And then there are sort of two modules that we add on top of that. There's something called core.compiler that basically has the code for type inference and some of our optimization passes. And then there's the base that that everybody knows and hopefully loves. Something interesting about it is so these are fairly isolated from each other. So when you add methods to things in base, you can go ahead and do that, that's fine, but we don't want it to change the behavior of the compiler. We want the compiler to still work and still do the same thing as much as possible, no matter what code people throw in there. So we want them to be pretty separated from each other. And to do that, they do this kind of strange thing where they each include copies of some of the same code, because they both need basic functions like arrays and tuples and all of that. They both need those to get stuff done. So they actually just they each include their own copy of that code. Now some people, I think, would say right away that this itself is bad, that there should be some way to not have to kind of copy, load that code in twice. And I can understand that, but I don't think that's that bad. I mean, it sort of makes sense. It's sort of like just having, two programs with similar text or something. That's really all it is. So they each need their own copy of it so they can, each specialize it against their own definitions. So that's not so bad. But something really interesting happens, which is that core also has this, this type. Oh, and yeah, I should clarify that the base and core compiler each have their own definitions of all of what you would consider the primitive functions, like the plus and minus and everything. They're totally separate. In fact, let me see here. Just a quick terminal. So in fact, we can see there's core.compiler plus, which you can see has 17 methods, but the normal plus has 166 methods. So these are different functions. Right, so this is a case where each of these is self-contained. They don't extend functions in each other. But there's one strange thing, which is that there's that type down there. And both of these modules need to define constructors for their types. But unfortunately, all of those methods are basically associated with that type. So for constructors, we can't avoid this. So this, this is, for instance, when for calling, when you write a type like vector int and you call it, it's those kinds of functions. So those are in fact shared between them. So everything is completely isolated and fine except for the constructors. They can see each other's constructors, which is, in practice, it doesn't really matter because the types are different, so they can be distinguished just fine. They're separated by type, but it's very annoying that we can't sort of isolate those method tables of the constructors. And we might eventually want some way to do that. So I find that kind of unsatisfying that there's just this one exception. So a bit more about types. So types have both representations and extents. So there's the way it's written, and then there's sort of what set of values it corresponds to. So you can have different ways to write equivalent types. So you can have a union of tuples or a tuple of unions, and those are actually equal. Or you can even do something like vector int, actually equal to vector t, where t is less than and greater than int, meaning it equals it. Although that's a less than or equals, of course. So you can have the same type with different representations. That's okay. But yeah, so these are but we have this we have different types to describe the different representations of types. So that one in the top left is a union, and then the next one over to the right is a data type, and then a data type, and then a union all. So we have types to describe the different representations of types. When people like to write functions like this, a function specialized for a particular type, f on this type, do this. It's very common. We write that all the time. And speaking of which, now in the missing type era, it's very common to see definitions like this, where people want to intercept, what if I'm in one of these cases where someone has a possibly missing value and they have like a union float missing or something. So they want to intercept that type, so they write that. But in fact, if you want to be stylish, you can write it like that second line instead, and they are actually exactly equivalent. Because if you think about it, if you can union any type, which might be any even, with missing, that just means some type that includes missing. So that can also be written as some t where t is bigger than missing. So this actually works. So please write it like that if you want to be stylish. And actually, I can show you, yeah, so actually I'll prove it. So type greater than missing equals type union T missing, where T is true. So those are equal. So I think that is not something that's bad about Julia. I think that's kind of cool. So yes, back to where I was. But then the problem is sometimes people also write methods like this, where they want to do something based on the representation of the type. Like, is it a data type or a union or so on? And the problem with that is this sort of drives the compiler crazy, because when you create a type, you have some type and then it's going to flow through the program, and eventually you're going to call some function on it. And, well, is it going to be one of the definitions of that kind, or is it going to be one of the second or third kind of definitions? So what was important about this type? Was its extent and meaning, or was it its representation? So the compiler sort of has to pick which one is going to matter, because otherwise it would have to be able to represent sort of both. It would have to keep track that, oh, I have a type that's equal to this and is represented as a data type, sort of the intersection of these things, which we could potentially do, but we don't have the ability to do, actually. So this is kind of annoying. And I think in 2.0, one of the things we might change is basically getting rid of the ability to write methods like that second and third one. But in the meantime, just, if you're doing that, please stop. All right, some more types and methods. So method specificity is really important in Julia. In fact, it's sort of weirdly important. Because what Julia does all the time at every function call is just call the most specific matching method. Call the most specific matching method. Just that's basically all it does, which is nice and simple and elegant, but it means this notion of specific is really doing a lot of work. It really, in some sense, sort of determines what your program does, because the specificity is ultimately in charge of picking, what method to call. And yet, it's sort of opaque how it actually works. Which is why I got this request from Tim Holy over there. And as we can see, this is assigned to me. So, reporting for duty. I'm going to try to tackle this a little bit. Well, sorry, Tim. There just are no rules. No. No, okay, I exaggerate. There are some rules. So the basic idea of it is very, very simple. So the basic rule is something is more specific if it is a strict subtype of another signature. So it's a subtype but not equal to it. And that's intuitive, right? It means that one is, fully smaller than the other, so it's more specific. This is the basic rule. So that's pretty easy to understand. This is what's doing most of the work. But then there are also more rules. And the next rule, I think, is best illustrated with a diagram. So Raz was telling me we need to use more diagrams. And so I'm taking that to heart. And I have a diagram to explain the next one. So the next rule looks a little bit like this. Unfortunately. So this might be something that's bad about Julia. So we kind of got into this situation. How did we get there? So there are a confluence of factors that sort of led us to the situation depicted in that GIF. So basically what happens is if methods have some overlap in the arguments they could apply to, but they don't have a specificity relationship, we need to give an ambiguity error. And ambiguity errors are annoying. We don't want to get errors at runtime, if we can avoid it. And people will often see an ambiguity error and they look at them and they think, oh, come on, obviously you should have picked that method. Why couldn't you figure that out? Because, people have these great, this great pattern matching ability that computers can't quite match. Maybe we should use machine learning for this, I don't know. Just have all of us, crowdsource clicking on methods saying which one we think is more specific. And just build a big machine learning model. I think that might work as well as what we have now. Good project idea. But so the ambiguity errors are annoying. But in balance to that, we need to be on the safe side, and in the compiler, we need to err on the side of assuming that things do overlap. And so that these are very much in tension. So if we want to reduce the risk of the compiler being unsound and messing up, we need to err on the side of assuming there is overlap. Because if it thinks that one method is callable and another one is definitely not, it will aggressively use that assumption. So we need to make sure that that can't happen if there's some possibility either method could be called. So being conservative demands that, but being convenient demands that we pick one to not give people an error. So those are in tension. And also, if you have two signatures that are very similar and it's kind of difficult to say which one should be more specific, maybe it doesn't really matter which one we call, And there have been some cases of this. There's sometimes people write definitions that are maybe sort of excessively manually specialized, like they'll, where perhaps from a more general definition might have performed as well, but someone just decided they'd tack on a manual specialization, so maybe isn't necessary. So in that case, it wouldn't matter which one you call. And it hasn't happened very often, but there definitely have been cases where we, had to switch the specificity rules a little bit, or change something in the compiler, and we did actually change which method got called in some of these weird cases, and I don't think anybody noticed. So, maybe it's okay. But in any way, this whole situation sort of begs for heuristics. That's why we've, every time someone has filed, hey, why is this an ambiguity? Clearly this method should be called. We kind of try to hack in, some new rules to make it work. And so this is some of the stuff that happens. So say we have these signatures, so a single abstract array or anything and an integer. So the first one is one argument, the second one is two arguments. So there's no overlap there at all. Those are totally disjoint because you can't have a call that has both one and two arguments at the same time. No overlap. So these we could say, it doesn't matter. One is not more specific than the other. But then let's say I add this method, abstract array and then any number of ints. So the first one is clearly more specific than the second because it's a strict subtype. And the second one is arguably more specific than the third because abstract array is more specific than any. An int is a concrete type, it's more specific than integer. So to the extent those overlap, int is more specific. So we have one more specific than two, more specific than three. But we also just said one is not more specific than three. So if we did it that way, this would not be, whatever kind of relation this is, it would not be transitive, which is, not a convenient property to have for some sort of ordering. So we kind of patched this up by actually making the first thing more specific than the third thing. So basically something can be a prefix, more specific than a prefix. So that kind of patched that up a little bit, and we try to make this a little bit transitive if we possibly can, to make the relation a little easier to understand. But now, all right, consider this type hierarchy. This is basically the same as the normal number type hierarchy we use, but I've just inserted abstract complex because I needed an additional complex type. So this is an example from Jameson. He discovered this and pointed this out to me not long ago. So we have the number type, real, then abstract float, then float, just like we have in normal Julia. And then we have abstract complex, complex, complex float 64 in this hierarchy. So now consider a bunch of methods. So let's go through this chain. So at the top, I have complex. Well, that is definitely more specific than abstract complex. Abstract is abstract. All right, and then abstract complex is a strict subtype of the next thing because the next thing just unions something onto it, so that's more specific. And now we have this union and then abstract float. All right, so let's think about it. So abstract complex and abstract float have nothing in their intersection. Nothing could be both of those. But float 64 is definitely more specific than abstract float. So if we had a float 64, we would probably want to call that third thing there because that mentions float 64. So that seems to be specialized for it. So we say, okay, that's more specific than abstract float. And then next step, abstract float is a strict subtype of that union at the bottom because it's just a strict subtype. So that's more specific. So we have this chain of 5 things, more specific all the way down. But then the problem is applying the same rule. Complex float 64 at the bottom is more specific than complex at the top. So we have a circle of 5 things that all want to be more specific than the next in a cycle. So this is a really unfortunate side effect of some of these heuristics piling up. This situation, I'm not sure if this actually happens in practice. It's kind of difficult to get into this situation. So I don't know how practical this is. I don't know if this really happens. But I think we're going to try to fix this. I think we probably could fix this, and I'm speculating that it's not likely to affect too much code because I don't think this really occurs. But we're going to try it, and we'll find out. And we'll see what happens. But so that this is kind of embarrassing, right? So I'm pretty much done. So in conclusion, Julia is not that bad. Yeah, I think that's the point that came across. Yeah, even the bad things often seem to work out somehow. But rest assured, we worry about it a lot. It could certainly be a lot better. We are always working on it. There's a hackathon tomorrow for a reason. Come to me, tell me your gripes. Keep posting gripes on Slack, and yeah, keep finding the issues. Keep the suggestions and ideas and issues coming. And thank you. Is there any time for questions? Oh, all right. Go to the mic, please, if you can. Yeah.
So the circular specificity chain that you showed, what happens today if that arises? Does the compiler crash, or do you get into an infinite loop?
Right. So so what would happen is you'd get basically implementation-defined behavior. Those would all land in a method table in some order, probably related to the order that they're defined in. And then some other parts of the system would assume that the relation is well behaved and would just use that assumption. And so basically it might be hard to predict what method would get called.
But that's not so bad.
But it's not so bad because it's debatable in the first place which method should be called in those cases. So you might not notice.
Good. Thanks.
Also on the specificity question, have you done any experiments to see what would happen if one were more strict about the sort of specificity rules? I imagine you must have. Does basically everything break, or how bad is it?
Yeah, so I have tried that. I opened a PR where I experimented with that a few months ago, I think, and it is pretty bad actually. If you start running into problems pretty quickly if you pull out our, some of the heuristics are maybe crazy, but some of them really make a lot of sense. So it is pretty hard to keep the system working if you really get too strict with that. Yeah, but we're going to keep working on it and try to clean it up as much as we can.
And just a quick follow-up: if one sort of does presumably one could use the existing Julia to write out the missing method that would have been called in the case where we use the current rules, but prepare for a world in which we use much stricter rules. Do you have an estimate about how big that list of methods would be?
No, I don't, but that's a very good idea. We should do that.
For the initial list of issues that you displayed, what's your priority for fixing those? Were they displayed in order of priority, or?
Yeah, they were not in strict priority order, but I think the compile time and time to first plot thing is definitely at the top.
Right.
So yeah, that was not in priority order, but we have an evolving notion of the priority of all those things.
What's your biggest gripe that's recently been solved?
Oh, my biggest gripe that's recently been solved. That's a tough question.
How about one that's not so recent?
Let me see. Well, I think probably the infamous 265 method invalidation thing that Jameson fixed is probably a good choice. Is it not still fresh in your mind how glorious that moment was?
I think now 265 is shorthand for referring both to the original problem and to the fix and the consequences of both.
Yeah, of course.
So
well, the fix has a much larger number that's harder to remember.
How much better or worse would the world be without unions?
Ooh, talk to Harrison. He definitely has opinions about that. How much better or worse would it be without unions? I think we could maybe get by without them if we replaced, if we had a better sort of trait-like system. I think we could maybe do without them, but I have to think some more about it. But I think they're nice. You know, the set theory concept behind it is very intuitive. It's very simple, so I find it nice. Okay, thanks.